Hi everyone, welcome back. Today we're going to finish up with this light propagation in fiber, this equation, and then simplify a little bit and get the analytical solution. And then we'll quickly move to another two physics process or Chi3 process in nonlinear media. One is Raman scattering, the other is Brillouin scattering. And after this, then we'll finish up with the third order nonlinearity, and we can finally move on to quantum mechanics related content. Okay, so to start with, I want to briefly review what we have learned in the previous lecture. Is that, the problem we're trying to understand is that if there's a pulse or if there's any light with the temporal profile sent into an optical fiber, and what would be the output? Okay, what would be output of this signal? And to solve this problem, we kind of assume that the form of your electrical wave of the light, okay, can be written as there's a function, cross-section function. If the cross-section is x and y, this is basically determined by the optical fiber itself. Okay, you have what we call the mode. And then there's a z and t, which is kind of like the amplitude that propagate along z direction and then change with time t. And then there's a propagation constant I beta naught z, right? Kind of like ikz. And if we do that, and then we use Maxwell equation and Fourier transform, a lot of stuff, and finally we arrive at this equation. Okay, this equation looks quite interesting. So this part is the propagation, right? We always have the partial amplitude, partial z in our nonlinear equation, and these two are coming from the dispersion of the fiber, that the refraction index depends on your fiber, and later we'll show that this term actually can be cancelled by doing a rotation frame transformation. And this term is our current nonlinearity term. You see that this is a squared a, right? So it's like in current nonlinearity, we know that the refraction index is proportional. Well, the refraction index is a term that is proportional to the intensity of light. Okay, and here we also know that the gamma here is defined as omega naught is the center wavelength frequency, and 2 is the Kerr coefficient, and c speed of light, s effective is the cross-section area, effective cross-section area of the fiber. And one thing I want to apologize a little bit is that I can feel that my English is is becoming worse and worse because I don't have any chance to practice them at home, and the only time I need to speak English is office hour teaching this class, and then my group meeting, and so in total it's like less than 5 hours a week. Okay, so sometimes I can imagine that at some point in this class I might get stuck, just because I couldn't remember one of the some sentences or some words. Okay, so when looking at this equation, one thing you might figure is that, okay, this one is a little bit difficult to solve, right? Because this is a partial differential equation. You have two variables. One is z, the other is t. Okay, and then what's worse is that the t has two terms associated with t, right? One is one is first derivative, the other is second derivative. And then also this equation is a nonlinear equation, and we know that nonlinear equation in general is very difficult to solve analytically. And typically, if you have linear equation, you should have one solution. If you have square term, then you should have two solutions. And this equation actually will have at least three solution branch. Okay, we call branch. Two of them are stable. Okay, and also depending on your initial condition and depending on your boundary condition, you might enter in one branch but not the other. Okay. So one thing, okay, before we go in and then provide an analytical solution to this equation, one thing is that for this fiber propagation equation, it is very common for us to transform this equation into what we call a propagation frame. Okay. there are two purposes for this transformation of frame. The first one is that it can actually eliminate this term, okay, which is actually great. The second one is that it actually make it much easier to interpret the solution of the equation. For example, here, okay, you have a, z, and t. Okay, so for this simplification, I will kind of cut the chase and get to the core of this. Is that think about there's one way that you can simplify the entire thing. Is think about this as a wave package. Okay, if it's a wave pack, and then what it does is that it would, suppose at t1, okay, it's at this place, and then at t2, the center would be at this place. So for the wave pack, it will kind of have a group velocity. What it means is that this wave pack travel as a whole, and then it will have an average velocity. So if you can move your frame, instead of looking at individual z and t, if you can have a moving frame, okay, moving along with the pulse, that you can always put the pulse at the center. If you can always put it at the center, t equals 0, okay, it's always your pulse center, then, okay, this entire thing becomes much simpler to analyze, right? Because if you want to analyze, okay, you want to analyze how the wave is behaving, then you always return to t equals 0. Okay, instead of here, if you just have a solution to this equation, then what you have to do is you have to figure out, okay, where is the wave first? Okay, before even looking at the solution, you have to know where the wave is. Okay, so how can we do that? The way to do this is actually by looking at what beta 1 is. Okay, what really beta 1 means. So beta 1, it turns out beta 1 is actually not dispersion. Okay, and we know that beta has a scale of wave vector. Okay, so wave vector is k, and then in k you will have k equals to n omega divided by c. And we know what beta 1 is, right? Beta 1 is simply partial beta, partial omega. Right? It's the expansion of beta, Taylor expansion of beta, and we call this beta 1. Okay, this term beta 1. So if you look at this and then you look at the k, okay, and suppose it's partial k, partial omega, then what it is n divided by c. It's actually c divided by n is the velocity divided by 1. Okay. So beta 1, if you understand k as refraction index times wave vector, or wave vector in vacuum, then beta 1 will have the dimension of velocity. We'll actually prove that it is indeed the wavelength. It is indeed the group velocity. Okay, so here we kind of, our assumption here, or our guess, is that beta 1 will equal to 1 over the group velocity of the wave pack. In other words, the wave pack will travel at the speed that is 1 over beta 1. Okay, so how does that convert into a propagation frame? So one thing we can do here, okay. One thing we can do here, because we want to put the wave package always at time equals 0. So what you can do is that, okay, if I want to look at the wave here as z knob, okay, and we know that, okay, the wave, we know that if we know the group velocity, then we know that the propagation time, okay, from 0 to z knob is always equal to z knob divided by vg. Right? So if we want to move the time into zero, then we should define a new time that is the original time minus your propagation time. Okay, propagation time. Then when you're looking at this wave pack here, okay, you know that at time equals 0, this wave will show up as z naught. Okay, will show up as z naught. Then at all the places, you only have to look at t equals 0 instead of finding a t. Okay, so here it can define as t minus z divided by Vg. Okay, this is the propagation time. You can also write down t minus beta 1 z, right? Because beta 1 is effectively is the group velocity of the system. Okay. Or the other word, you have t equals capital T plus z Vg. Okay. Now let's make the transformation in the equation. So in the equation, instead of writing an equation for partial a, partial z, instead of solving a, okay, instead of solving this AZT, what we are going to solve is a capital Z, well, Z capital T, right? Because T is the frame that put the pulse in the center. So what we can do is that first we can replace all the T with capital T. This is simply because we're choosing a different frame, right? We can replace that. But when you replace that, make sure that all the small t will also become capital T. Okay, so that it becomes partial a zt partial z plus beta 1 partial a partial t square a zt Okay, so you might wonder, okay, does this make any sense, right? You're simply replacing the variables with small t to replace small t with capital T. But here, one thing that we should pay attention to now is that this one, okay, because right now your capital T is actually a function of both t and z. Okay, it's actually a function of both t and z. So what you can do here, we're going to write here, is we write it down as t minus z Vg. Right, so you can see here is that because the change of the frame, your frame itself contains the position, the location information. Right, it's a function of the location, so that when you do the derivative on z, not only should you do it here, but you should also do the derivative on the z, right? So we can calculate that here. What we're trying to calculate is partial a z t minus z Vg partial z. Right. So for this one, what you can do is that you can use the chain rule, right? Partial z you can use the chain rule, which is a partial z. Okay, this is the original one, plus partial a partial capital T, right, capital T here, and then T partial Z. Okay, maybe we shouldn't write it down as this one. Just write down as capital T. It's always a little bit confusing when you're trying to do a propagation frame and then two variables, are related together. Right? This is a chain rule, right? You get derivative of z on itself, and then whatever other variables you have, okay, you do a derivative of on t and then t on z, right? And what we have here is partial t partial z equals to this one, partial t partial z minus partial z vg, well, z divided by vg. And we know that t and z are two completely independent variables, right? You can choose arbitrary z and arbitrary t. They're not related. So the first term is 0. And the second term, right, your differential of a linear z. So the net result is minus 1g, okay? And then by definition, if you define vg equals 1 over beta 1, then this one will be minus beta 1. Okay, so what will you have? You will have partial a, partial z, and then minus beta 1. Okay, this is minus beta 1 come from here, and partial a, partial t. Okay, and you see here the minus beta 1 will cancel out with the beta 1 here. Okay. You cancel out with the beta 1 here. So then you plug this in, and then this term will reduce to okay. So when you do this partial a partial z, you don't have to worry about capital T now, because here you can treat capital T and z as independent because you already use a chain rule, okay, to separate. So this equation now looks, at least, okay, in my mind, much easier, much simpler than the original one, okay, because you now only have each variable only have one differential. And this equation, okay, is actually called nonlinear Schrodinger equation, and I will explain why, okay. The reason is that if you multiply I on both sides, okay, multiply I on both sides, and this is minus, okay, and then let's move this to that side, okay. So if you multiply I on both sides, you will arrive at this form. And if you're familiar with Schrodinger equation, we know that Schrodinger equation actually looks like I partial psi partial t equals to the Hamiltonian times your wave function. And in many ways, the Hamiltonian, if we are in one-dimensional space, then it actually is this. Okay, and then plus the potential energy. So this is Schrodinger equation. So you can see that the similarity here, right? On this side, it's I, complex number, partial a, partial 1 derivative, partial phi, partial another derivative. Okay, you don't have to really, you don't have to worry too much about the indices here, right? Here is position, this is time, but in a general coordinate, you can just think about them as variables. And then the second term here is the second derivative of another variable, right? Here is capital T, here is position z. And you might think, okay, there's a minus sign here, but keep in mind that the beta 2, because it's group velocity dispersion, for material at certain wavelengths, this can be a negative number, right? So you can actually match these two of the sign, okay? And then finally is this nonlinear term here, right? So if your potential well has it's not really a potential well. If you have nonlinearity in here, which usually means particle interaction, then you will actually have exactly the same form as this one. So both of this equation, okay, this is actually the same as this one, is the same as nonlinear Schrodinger equation. Okay, nonlinear Schrodinger equation. And you can also think about this. The similarity here is actually very interesting. Suppose there's no Curry effect, right? Suppose there's no Curry effect, just dispersion. These two equations can be identical if, right, no nonlinearity and then no potential well. Okay, so what the Schrodinger equation means is actually you treat an electron as a wave, and then suppose there's no potential well, then this is a free electron propagating. Okay, free electron propagating. And now what about this equation if there's no nonlinearity, and this one is dispersion? Okay, so what you have is you have an optical pulse, or you can, in this sense, consider it as an optical particle that travel freely or propagate freely in an optical fiber. And these two will have the identical equation, okay, which means in some way you can simulate the Schrodinger equation with your optical system. And also the other thing to think about here is that the beta 2, the dispersion, okay, is actually, you can consider it as an effective mass, okay, effective mass. And it decides how much inertia you will have in your optical pulses. And in the next section, we'll use this nonlinear Schrodinger equation and then get an analytical solution. Okay, and then to show you that indeed, okay, there's particle-like solutions exist that resembles the Schrodinger equation solutions. Okay, so let's come back and see how to solve this equation. I want to be very clear before digging into the mathematics here what it means for this equation when we do this propagation frame. What it means is that if there's a pulse sending into the fiber, then your time frame is actually moving at the exact speed with the pulse, right? So if your pulse is moving at speed of light, then your frame is also moving at the speed of light. And that would change, that would do is that if suppose there's no dispersion, there's no nonlinearity, then your pulse will always sit at the center of t equals 0. Okay, capital T equals 0. And it's because, right, the time always minus your propagation distance divided by your propagation speed. Okay, so if your solution, whatever solution you have, if you set beta 2 equals 0, lambda equal to 0, gamma equals 0, and then your solution is not sitting at the center, that means your if your initial condition is at the center, which you should, if your answer is not sitting at the center, that means you made some mistakes in your calculation. Okay, so there are literally numerous solutions to this equation, and then I think there's thousands of papers published trying to solve this equation. And myself, actually, I have several papers on, there's perturbation terms add to this equation, and then what will happen to the optical pulse, but of course not in the fiber, in a microresonator. Okay, so a standard solution to this is that AZ T equals to, there's amplitude of your wave, we call B, and then it's a secant function. Okay, T, tau, you can think of it as a pulse width. Okay, and then there's a propagation constant, where delta you can think about it as the propagation beta or k. And here, to make things really simple, we can say b is real number. Okay, and this form of solution is just one of the possible solution. It's called soliton solution. And this is heavily started in the 1980s because people try to use soliton as a way to transfer information. And if you look at this solution, one thing you realize, okay, first of all, let's write down the definition of sec. Sec x is defined as 1 over cosec x is 2 ex plus e minus x. Okay, so you can see that it will reach a maximum at x equals 0. Okay, it's 1. And then what it would do is that if x is larger than 0, then this exponential term will quickly dominate, and then the entire value, okay, would drop very quickly. If it moved to, x is an active number, then this term will explode exponentially, and then the number will also drop. And so you can think about it as this way. Okay, this is x, and then it kind of look like this. And let's see if this is t. Okay, let's see for t. Okay, and then this width is actually tau, right? If you think about it, if you increase tau, right, then your capital T can increase to reach the same amount of x, right? So the larger the tau, the broader your pulse. The smaller the tau, the narrower your pulse. So tau characterize the pulse width. And also, like, this is a great time, okay, for engineering student and physics student to look a little bit more into exponential, because some of the very important things in our life is happening in an exponential way. So the important thing about this solution, okay, why we call it soliton solution, is that this solution, if you look at it, the pulse width tau, it doesn't change with your propagation distance z. Okay, this is something really, really interesting. Tau does not depend on z. Okay, and you might think of, okay, this is just steady state solution. What's so different about this solution? Because if you think about it, since there's dispersion here, and in the optical pulse, different wavelengths will travel at different speed. So naturally, your pulse, okay, should broaden. Okay, if this is z, and then naturally your pulse should broaden because some of the part travel faster, some of the part travel slower. Okay, so it's very natural for the pulse to become broader, and very rare when your pulse remain unchanged. And the other thing to think about it is that in terms of entropy, right? So having all the energy concentrated at one place is actually having a really, really small entropy, because things are in extremely order, right? If you think about the particle, if you think about the photons in this beam, right? The maximum entropy would be the photon is everywhere, right? It's just kind of like a continuous wave. So having all photons in one place forming a pulse is something that is against the maximum entropy law, right? So it actually takes extra effort to do that. And this one is actually a very, very special situation where we say that your dispersion term, which wants to broaden your pulse, and then your current nonlinearity term, which also wants to broaden your pulse. If you neglect this term and then you plug in the solution, you can find this term also try to broaden your pulse. But they two somehow magically balance each other. And then let's plug this in, okay, just to show you how this is done in a mathematical way. And so let's do this derivative term by term, right? So the first one is fairly straightforward. You had derivative of z, that will give you I delta coming into the front, right? And the rest is unchanged. So I delta I times with this I here, so you acquire a negative sign minus delta A zt, right? So this is the first term. And let's look at this last term. The last term is also relatively simple, right? So you have gamma A square A, right, equals to, you just square all this, and then because it's magnitude square, so that your propagation phase term goes away, then you have, and then also we assume B is real, right? So this is minus gamma is the coefficient, B square, okay, and then secant square, and then A, right? This is relatively straightforward. And then the last one is a little bit trouble because you have to do derivative of secant and twice, right? Second order derivative. And this one, you can do it with Mathematica, and I won't repeat the process here, but I can write it down as partial x of a secant square of a secant function will equal to 1 minus 2 secant square x secant x. Okay, so let's put it down here, beta 2, okay, beta 2, this one equals 2 beta 2. And then whenever you do derivative, using the chain rule, this one will come out, right? So that you will have tau square, right? You do second derivative, so tau come out twice, tau square. And then all this coefficient left unchanged, and then combine with this secant, and it returns back to A, okay? So then what you will have is 1 minus 2 secant square t divided by tau A, okay? You can pause the video and then check the notes. In the notes, there is a very detailed mathematical derivative that you'll be convinced that this is correct. So now if you look at this equation now, okay, if you look at this equation now, and if we move everything to the same, if we move everything here, then this one will be minus delta A. Let's see, we put everything on the right hand side, so that you will have 0 equals to delta A, delta first, right? Because all the terms have A, right? So you can put the A at the end. So delta is the first term, and then this one plus beta 2 tau square minus 2 cancel each other, beta 2 tau square secant square, and then the third term is this one, also minus gamma b square secant square. And then this entire thing, okay, everyone has an A here, right? A. So this entire thing equals 0. So now you can see that how this can be balanced, right? There's 2 secant term here. So this 2, if you choose the correct, so beta 2 and gamma are, constant. You can derive from the fiber, right? So they're fixed once your fiber is, when you select a certain piece of fiber. Then the thing that you can change is actually B is the amplitude of your pulse, and then tau, which is your pulse width. So you see that if B and tau satisfy a certain relation, okay, then you can have these 2 terms cancel each other. And the other one would be once you know the tau, right, and then these 2 are just 2 numbers, and then they can also cancel each other, meaning that your delta, your propagation constant, will be related to tau. Okay, so if we do this, and then we can have a solution, would be we use tau as our primary variable, 2 tau square. Okay, this is your beta. This is your delta. And then you have these 2 terms equal to each other, so beta 2 tau square plus gamma b square equals 0. Okay, equals 0. So the first thing you notice is that because b square and tau square are both larger than 0, and gamma, okay, gamma is a nonlinear coefficient, and N2 for for all materials is actually larger than 0. Right. So for this solution to have non-trivial solution, then you have to have beta 2 smaller than 0. Okay. So this is actually the first meaningful result coming out from this solution, is that if you want to have a soliton, if you want to have your pulse propagate in the fiber and doesn't change its form, then you have to have a negative dispersion, which we call anonymous dispersion. Okay, anonymous dispersion. And once you have anonymous dispersion, then you can solve B. Okay, you can solve B. So overall, the solution would be AZT okay, there's a propagation constant. Okay, so this is a solution that satisfies the nonlinear Schrodinger equation. And there's only one free parameter in this waveform, that is the pulse width tau. Right? So once your tau is fixed, right, you select the tau. If you want this to be a steady state solution, you want this pulse to not change its form, to typically not change while it's propagating, then you have to select a correct amplitude. Okay, if your amplitude is too high, it won't do that. If your amplitude is too low, then it won't do that either. So you have to go with exactly the correct amplitude. I just found out that the sun changed position outside my room, outside my basement, so that the lighting condition actually changed dramatically while I was recording this lecture. So maybe, okay, just maybe, some part of this video, probably 10 or 20 minutes of the content would be quite noisy because there's not enough light and I didn't change the camera setting. And anyway, let's come back to the class. So this is a solution, and this solution means that your soliton wave will not change its form, will not change its shape when it propagates along the fiber, which is very attractive for for communication purpose, because each soliton pulses can represent one information bit. Okay, but let's look at this. This solution is acquired in an ideal case of the fiber where we assume there's no loss, which fiber always have loss no matter how small it is, and we also assume that the amplitude is perfect, right? We said the amplitude is, you need this amplitude to become a soliton, and let's say the input amplitude is exactly as what you're required. So let's look at these two situations where, okay, if we have loss, or if we have input too much power or too little power into the fiber. Okay, so the way to analyze this, there are several ways. Okay, you can add a loss term here, and then to solve the use perturbation theory to solve that, and that's perfectly doable. You can use Lagrangian perturbation method, or you can use, or you can simply use momentum analysis method. But here we use a very, very simple way to do that. Okay, is let's consider what is the power. Okay, because the loss is on the energy of the pulse, right? So let's consider what is the energy of the soliton. Right, the energy of the soliton is that you should integrate. Okay, your energy, well, this is your pulse envelope. And a square, a is the field, a square gives you the intensity, right? So if you square it and then integrate all of that, then you will actually get your pulse energy. And I can do this for you guys. Okay, just integrate this, and then you'll get beta 2 gamma tau, right? So it's a function of tau, which is what we kind of expect. So if you have loss, then your solitons, then your energy of the soliton should decrease, right? The loss equation would be, right, your loss is, the rate of the loss is proportional to how much energy you have. Okay, and we know that the solution would be exponential decay, right? Okay, so let's say if you originally you input exactly the correct amount of energy, okay, into the fiber, then after some propagation, okay, you actually lose some energy. And you might wonder, okay, what does that mean for the soliton? What does that mean for the soliton? Does that mean that it's no longer a soliton, or does it mean the soliton changed its form? So what really happened is that if now you have a smaller, let's say at position Z, your energy is smaller than your input energy, then what the soliton would do is actually very interesting. It will keep the soliton form, but then it will reduce, okay, the soliton will increase its tau. It will actually increase its tau. We say tau Z. So tau Z will increase so that the soliton energy will match whatever energy is left in the fiber. Okay, and this way, okay, this way is very interesting. Is that this way the soliton pulse actually maintain as a soliton. It just become a little bit broadened, depending on how much energy is left. And this thing is I'm not so sure about. This thing is actually introduced in a lot of nonlinear optics books. I'm not sure if anyone has observed this yet. But in optical microresonator, okay, in microresonator, we actually observed this in 2 years ago, and then what we see is that the soliton indeed, when we turn off the pump and let the soliton experience the loss, then we see the soliton become broader and broader, but it's still a soliton. Okay, so this is very, very interesting. Okay, so it's a little bit counterintuitive. You might think you might think if the you have loss, then your amplitude would drop, but keep the pulse width the same. But the thing is that the pulse width will become broadened, okay, and also when you're broadened, then your amplitude, of course, will drop a little bit to keep the energy, okay, equal to the soliton energy. And the second one is, let's say, what if you input too much power? Okay, which is always possible, right? Which is always possible. So what will happen is that your soliton, if the power is not that much higher, okay, if it's just a little bit higher, then what the soliton would do, just as the same, just as the same same analysis, is that the tau will decrease. Right. So a way to understand this is that, okay, if this is a soliton solution, and then you're inputting, the same amount of, you're inputting a pulse that has the same tau, but then the amplitude is much higher, then what the soliton would do is that it will actually become narrower. Okay, it will actually become narrower. Okay, become narrower because that way the soliton energy can match with your input energy. So the way you can think about it is that it's kind of adiabatically adapt your input into a soliton form that can propagate steadily. So this is really, the soliton solution is really like a steady state solution, and whatever you put in there, you try to smooth into the steady state solution. So when you have tau become decreased, okay, the pulse become very short. By Fourier transform, we know that delta tau, okay, delta omega, okay, you can say delta tau times delta omega 2 pi, right? If you have a very small delta t. Okay, and this is tau, you can think about it. So if you have a very short pulse width, then what will happen is that if this is small, then in frequency domain, if you do Fourier transform, then your spectrum will become broader. Okay, your spectrum will become broader. If your input is this, then if you input too much energy, then your spectrum will become broader. And this is actually one of the techniques that people use to expand the optical spectrum of a pulse. Okay, it's just send a lot of energy, okay, into a fiber, into a piece of fiber. And with the fiber, it's really good. Let's say if the fiber has very large nonlinearity, okay, that can come from either the material or you can have a very small core area. Okay, then what will happen is that this process becomes very, very efficient, and then the optical span, the frequency span, can increase like by an order of magnitude. Okay, and this is one of the very popular technique that was developed in the late 1990s, and then eventually led to the invention of optical frequency comb, and then won the Nobel Prize in 2005. Okay, so this is the optical solution, optical soliton, and then the equation, and we'll now move on to the final topic in third order nonlinearity. It's a Raman physics, Raman scattering, and then the Brillouin scattering. Okay, so for the Raman scattering process, it's also a chi-3 process. That's because we're kind of a little bit slow in terms of where we are. Like ideally, I'm actually thinking we should be moving towards quantum today. Raman scattering process. So for this process, the Raman scattering and Brillouin scattering will be very quick, and then only focus on the physics picture, and then briefly mention how to formulate them. Okay, so the Raman scattering process was actually discovered in 1920s, way before the framework of nonlinearity occurs. So what people found is that, okay, if you have a material and then you input a light of omega knob, then what will happen is that at the output you will see omega knob as transmitted, but also we have omega prime, and then omega prime is smaller than omega knob. Okay, it's smaller than omega knob. And then this omega prime, the difference between omega knob and omega prime really depends on different materials. It really depends on different materials. And then you will actually have multiple omega primes here. Okay, so in the experiment, what you will see in the frequency domain is omega, your input here, omega knob, and then you will have a series of scattering here as omega prime. And this is your output. Okay, input and output combine these two, right? So this is discovered in the 1920s, and the people name it Raman scattering because it looks like some of the photon is scattered from one frequency to other frequencies. And later people really understand, okay, what this process is about. What it is that there's inside each of these materials, okay, if you look at individual molecules, for example, we can have water molecules, H2O. Okay, H2O. If you have light coming in, and what will happen is that, okay, these water molecules, they can do vibration, okay? The O and H bond can get closer, wider, closer, wider. There's a vibration degree of freedom, and also the molecule can do rotation, right? So all of those would actually give you energy. All of those can actually consume energy. So the actual process would be, okay, if you have a photon coming in, hit the molecule, and then what will happen is that the molecule would take some of those energy, okay, and let's say transform it into vibration. Okay, in this sense, it's the OH bound vibration. And plus, because there's the energy conservation law, right? And plus a frequency that is slightly lower than the original one, okay? And this oscillation or rotation of the molecule, and is really responsible for the Raman scattering process. And another way to understand this is that people can put in, okay, we call the energy state diagram, right? You have a ground state, okay, for your molecules, right, which is a ground state, and then you have an imaginary state, right, which is H bar omega knob. And after excited to this state, the molecule might not return to its original state. Instead, it returns to an intermediate state or excited state where it takes some energy and start to do vibration, start to do rotation. And then, so this one will be H bar omega prime. Okay, so part of the energy goes to the next photon, and then part of the energy stay in this vibration or rotation scheme. And the Raman scattering process, if you look at it, okay, you might think, okay, this is not useful, or this is just a little bit not efficient, because you kind of have to rely on the molecule. There's actual energy transform between light and matter. So that the process might not be as efficient or might not be as rapid as the fourth mixing process. But it turns out the Raman scattering process is probably the one of the most heavily used nonlinear process in our daily life. Okay, what people can do with this Raman process is that they can use this as a way to do spectroscopy, to see what type of molecules you have. Let's say if this is a black box, right? You don't know what molecule it is. Then you can actually look at, you can actually look at how the light is scattered. And then because each peak here represents a certain bound, certain type of vibration or certain type of rotation, then you can actually use this scattering as a fingerprint of molecules and really measures what type of molecules do you have in your sample without without breaking all those bounds and then see the composition of elements. Okay, and one way you can think about this is that you can tell the difference between water and other molecules, for example CO2, water and carbon dioxide, because carbon dioxide. Okay. Let's put it this way. The way to think about this is that for carbon dioxide, because the molecules are much more heavier, right? So you can imagine that the oscillation frequency of this must be lower than that, right? Because you can think about it as a harmonic oscillator. Okay, if your particle is heavier, then it has more inertia to move. Okay, then thus you take less energy. So it's actually very easy by using Raman spectroscopy to tell the difference between water vapor and carbon dioxide, because this one will have featured scattering frequency very large here, and then this one will have a much smaller frequency difference here. Of course, the real experiment is never a single line. There's multiple lines because you have different energy state or multiple energy state in vibration, and also you have to consider rotation. Okay, so this one has been commercialized. You can buy Raman spectroscopy. Actually, I think UVA lab has one or two of this, and if you ever work in the clean room, you probably have used it already. Okay. And now let's look at how to formulate this. In the very beginning, before people even know that there's a nonlinear optics framework, people already measured this experimentally, and what they found is that the intensity of your Raman light, if you're propagating inside the black box, and here is Z, equals to, there is a gain coefficient depending on material and also depending on the, mainly depending on material, is proportional to your input light, let's say I in, also proportional to your Raman light, also proportional to your Raman light. This is measured experimentally, and of course, in our nonlinear optics framework, we never write down equation as we never write down equation of intensity. We always write down equation as a field, right? So there's actually a standard way to convert intensity to field. And one thing is that you can define, I, defined as A squared divided by S. S is the mole area. A, you can normalize it to A squared is the power, so you can drop all the coefficient in the front. Then what you have here is that you have d AR squared dz, G, and then there's a S on this side, but there are two S on this side, so you have G divided by S effective, let's say, And let's assume that the S is the same for the input light and the Raman light. That is not always true. That is not always true, because if the Raman and the Raman light and the input light frequency is very different, then usually there is a small difference in your effective area. And so here is A in square times AR square, right? And so here A in square, probably we don't need to change that, okay? Because we can assume that A in is very strong, right? So we don't even have to have an equation for A in. We can assume that A in is much stronger than AR, so that you don't have to worry about any change in A in. Okay. So to change this is still an equation for intensity, right? We just change the parameter from I to A square. It doesn't have any new physical meaning. So one way to do this is to actually see how we can formulate this, right? So if you write it down, okay, if you write it down, dAr square dz is actually equal to dAr conjugate dz, right? So this is equals to actually equals to AR star dAr dz plus AR dAr star dz. Okay, so this kind of look, if you try to remember, if we recall what we have in solving energy conservation for harmonic generation, for some frequency generation, you probably would remember that there, okay, because we try to convert from field to energy, what we do is that we multiply field conjugate to the original equation to convert that into energy. So here we have a similar situation here, right? You can, but in a reverse way, right? You have equation for energy, and it can actually be two separate equations, one equation for AR, the other equation for AR conjugate, okay? So because of this, we can make a guess, okay? We can make a guess. We can guess we have dAr dz equals to G as effective A in AR. Okay, and then this equation will have a conjugate. Okay, and then we add a 2 here. Okay. And then what you can do is that the first equation multiply AR conjugate, second equation plus second equation times AR. Okay, and in this way you will have AR conjugate dAr dz. Okay, first term on the left hand side, second term on the left hand side will be AR dAr conjugate dz. Okay, on the right hand side you will have G2 as effective. Okay, A in. This is a common term for both of these. And then you will have AR times AR conjugate, so AR square. AR times conjugate times AR, so AR conjugate. And we know, okay, this is this, then it goes to DAR conjugate DZ, okay, equals to these two, sum together, there's a factor of 2 here. So G S E F F A in AR. Okay, and then if you assign, okay, if you multiply SEFF, 1 over SEFF on both sides, okay, and you return to exactly this equation of energy. So for Raman process, okay, if you only care about the field, if you only care about the intensity, then you should write the equation like this. Just use this equation. It should be good enough. If for some reason, for example, like light propagation in a fiber, right, you have to consider other effect that mostly depends on field, like Curry effect. Then when you add the Raman effect into those equations, you have to use field. And when you use field, this is how you add the term into there. Okay. Okay, so let's at the end, let's spend 10 minutes to quickly talk about Brillouin scattering process. Most of you, I imagine, would never really encounter this. You might see this, but you don't. Usually people don't realize it's actually from Brillouin scattering. So Brillouin scattering, what it is that, okay, if you input a photon into material, and then let's say this is a lattice of the material. And what will happen is that the photon give away some energy to the lattice. Let's see. And then the lattice start to vibrate. Let's say stretch a little bit, right? It's hard to. Okay, the lattice start to, let's say, vibrate a little bit. And what this vibration is, okay, is in terms of quantum, is phonon. Okay, you can also understand this as sound, right? So it will also have, the phonon will also have frequency, okay, and let's call it capital omega. So the Brillouin scattering process is similar to the Raman process, that it actually has to give away some energy to the material, okay, and you wouldn't, and also the output frequency shift slightly. And the critical difference between the Raman process and the Brillouin process is that in the phonon, okay, in phonon actually carries a lot of momentum. So when we're writing down this process, we're not only required to satisfy the energy conservation, but we're also required to satisfy momentum conservation. So let's write down the energy conservation first, which is fairly straightforward. The input energy is h bar omega equals to h bar omega prime, the output frequency, plus the frequency of the phonon, right? And then the momentum conservation law would be the input is h bar k, okay, equals to h bar k prime. This is this frequency, that momentum of input light, output light, plus, let's say, the momentum of phonon. Okay, and then in quantum mechanics, we can show that the k, or the wave vector, or the momentum, always equal to, in this sense. Let's for simplicity, let's not include refraction index. Okay, is omega divided by your speed, right? Omega divided by your speed. Then what this would do is that it would be omega divided by speed of light. Okay. Let's still include the refraction index. Speed of light minus, okay, move this to this side, omega prime. Omega prime is omega minus capital omega, right? You can look at it here. Omega prime equals omega minus capital omega divided by Cn, right? and then equals to this side, it requires the phonon is capital omega, is its frequency, divided by the speed of the phonon, which is the speed of sound, okay? Speed of the sound. So the left-hand side, if the left-hand side, you will cancel these two terms, and then you end up of capital omega divided by Cn equals to capital omega divided by velocity of light, velocity of speed. And you know that, intuitively you know that this equation will never be satisfied, right? Because the speed of light is on the order of 3 × 10 to the 8th meter per second. The speed of sound in the solid, let's say in silicon, right, is roughly 5 × 10 to the 3 meter per second. Right, so there's a huge mismatch here, and this equation will never be satisfied. And of course, you might think, okay, this is great. We don't have to consider Brillouin scattering process anymore. But the fact is that it still happens, and how? Okay, the way is that if you think about it in a momentum picture, is that the momentum for the light is relatively small, right? But the momentum of the Brillouin scattering is very large. The momentum of the phonon is very large. So if we do the difference between input and output and of the phonon, right, and then of the photon, right, and the difference would be left for the phonon, and this one will be very small. So instead, what you can do is that, what if, okay, especially in fiber, what if the generated light, the output light, is actually being reflected back. And this way, okay, when you have input minus output, you will have the entire input minus output, okay? You have the entire thing as your momentum for the phonon. Okay, so the Brillouin scattering, okay, in most cases happens that the light is being reflected back. Light is being reflected back. And let's see if that would work, okay? So if it's reflected back, then you have input momentum h bar k, and then the output light is reflected back so that you have a negative sign on the momentum direction, and then plus h bar omega. H bar k phonon. Okay, and then you cancel all the h bar, and then you will have omega Cn plus omega minus capital omega Cn equals to omega velocity of sound. And then we can assume that capital omega is much smaller than the optical frequency. That makes sense, right? Phonon frequency is usually, you can get it at megahertz, gigahertz, but it's never going to be like hundreds of terahertz of optical frequency. So this side will roughly equal to n omega divided by c equals capital omega divided by n, divided by velocity of sound. Okay, so now it starts to make a little bit sense now. So what will happen is that depending on your material's velocity, depending on material's sound velocity, you will acquire different Brillouin scattering frequency, right? So your frequency of Brillouin scattering would be 2n omega times v divided by c, right? So basically 2 times your original frequency divided times the velocity difference. Okay, so if we use the fact that if we're at 50-50 nanometer, then omega divided by 2 pi would be 193 terahertz. Okay, and then we use refraction index of 1.45, and then the speed of the sound for silica is 5.6 meter per second. Then what will happen, okay, here what will happen is that omega for silica will roughly be 10.47 gigahertz. Okay, 10.47 gigahertz. Okay, so this is a relatively small frequency. So let's plug this in and then think about this physics picture here. Okay, if you send light into a fiber which is made of silica, then what will happen is that it will give some energy to the phonon. Okay, and then part of the light, okay, if you give energy to one phonon, then one of the photon will be reflected back. Okay, will be reflected back. And just like Raman process, okay, the more input you have, the more reflection you will have. This is a nonlinear process. So what will happen in your lab, okay, if you buy a long spool of fiber, and then you send a lot of power, let's say tens of milliwatt or hundreds of milliwatt into like kilometer long fiber, then what you will see is that if you increase your input power, then you will see more and more loss of your fiber. And those are actually not, you might think about it as, okay, am I burning my fiber? Actually, no, it's just a lot of light is being reflected back. And if your laser or if your amplifier doesn't have an isolator to kind of block all those reflected light, then this process can be potentially dangerous, okay, to your laser, and can damage your laser because of this reflection. Okay, so that is all for today. The key difference between Raman and Brilliant is that Brilliant requires momentum conservation, and because of that, most Brilliant effect happens with the backward scattering. Okay, thank you.